A quadrilateral has all integer side lengths, a perimeter of 26, and one side length of 4. What is the greatest possible length of one side of this quadrilateral? Well, we can just draw a quadrilateral like this, and the point of doing this is to split it into two triangles. Note that the quadrilateral is concave rather than convex. We can still do the same thing, so it's not a big deal. For example, we could split it like that too. But let's just focus on the convex quadrilateral for now. So we know that one side length has length 4, so we'll label that. And from here we can just test out the answer choices. So we'll start with the largest answer, 13. And we'll set AD equals 13. And that means that we must have the equation inequality is smaller than or equal to 16 because of the triangle inequality. And we have BC plus CD must be equal to 9 because the perimeter of the quadrilateral is 26. Now, due to the triangle inequality on triangle BDC, we know that BD is going to be less than or equal to 8. Now we know that if BD equals 8, this still can't be possible. Because if we set BD equals 8, we must have AB plus BD is larger than AD. But if BD is 8, 4 plus 8 is less than 13. And if BD is even less than 8, then of course 4 plus a number even less than 8 will be still less than 13. So ABD wouldn't form a triangle. Therefore, the answer can't be E13. So now we go on to a different case and we try the case where AD equals 12. So in this case, if we write 12, we have BD is less than or equal to 15 because of the triangle inequality on ABD. And we have BC plus DC equal to 10 because the perimeter of the quadrilateral is 26. So from here we can deduce that BD is less than or equal to 9 because of the triangle inequality on BCD. So if we have BD equals 9, then we know that ABD satisfies the triangle inequality because 4 plus 9 is larger than 13, and the other two inequalities are satisfied too. And if BD is less than 9, well, it doesn't work, but we know that BD equals 9 does work. And in this case, if we wanted to, we could just set something like BC equals 6 and DC equals 4. And we know such a quadrilateral must exist because the two triangles it's made up of, ABD and triangle BCD, both satisfy the triangle inequality and they share a side, which means they form a valid quadrilateral. So our answer choice is D, 12. How many digits are in the base 10 representation of 8 to the power 5 times 5 to the power of 10 times 15 to the power of 5? Well, first of all, we can write this expression in its prime factorization. So we have 2 to the power of 3 to the power of 5 times 5 to the power of 10 times 3 to the power of 5 times 5 to the power of 5. And we want to group the 5's together, so we get 2 to the power of 15 times 5 to the power of 15 times 3 to the power of 5. And we want to group the 2 and 5 together because it'll form a 10. And so we get 10 to the power of 15 times 3 to the power of 5, which equals 10 to the power of 15 times 243. And we know that multiplying something by 10 to the power of 1 adds a 0 to the end. Multiplying by 10 to the power of 2 adds 2 zeros to the end. So multiplying by 10 to the power of 15 will add 15 zeros to the end. Meaning our answer is the number of digits in 243, which is 3, plus 15, which is 18. So our answer is 18. An integer is assigned to each vertex of a cube. The value of an edge is defined to be the sum of the values of the two vertices it touches. And the value of a face is defined to be the sum of the values of the 4 edges surrounding it. The value of the cube is defined as the sum of the values of its 6 faces. Suppose the sum of the integers assigned to the vertices is 21. What is the value of the cube? Well, let's just draw the cube first. I find it helpful to visualize. And we know that we're going to have 6 faces. And if we look at just one edge of the cube, we'll see that each edge is on 2 faces. Since we add up the sum of the faces to find the value of the cube, and each edge is on 2 faces, we know that each edge is counted 2 times when we're calculating the value of the cube. We just want to look at one vertex of the cube, which we see is on 3 edges. So for each vertex, it's on 3 edges. Each edge is counted twice. So therefore, each vertex is counted 6 times when we're calculating the value of the whole cube. And we know that the sum of the integers assigned to the vertices is 21. And each vertex is counted 6 times. So our total answer is 126, or D.